Welcome back to the PFC podcast. The views and opinions you are about to hear are the speakers and do not necessarily reflect those of anyone else. Now on to the podcast.
Welcome back to the PFC podcast. This is Dennis, and this episode was recorded with the sponsorship and support of the Special Operations Medical Association. Thank you guys very much, and I hope you enjoyed the talk.
Today we'll be discussing countering the electronic warfare threat through modeling electromagnetic signatures of portable ultrasounds used in far-forward environments. We have nothing to disclose, and the views expressed in this presentation are that of the authors and not of any position or policy from the Department of the Army, DoD, or U.S. government. Now, we're all familiar with the electromagnetic spectrum, but to kind of orient you to the slide, we're going to start with gamma rays, which are going to be the shorter wavelength with a higher frequency and higher energy, continuing on into the X-ray and the ultraviolet spectrums, and then that small visible spectrum, which allows us to see color. Then we're going to continue on into the infrared and then microwave spectrum. But for the purposes of this presentation, we're going to mostly discuss the radio spectrum, which is going to be a longer wavelength with a lower frequency and lower energy. Now, this is another depiction of this electromagnetic spectrum with a larger emphasis on the radio spectrum. Now, for context, our Harris radios predominantly work at that HF realm to higher end of it, or predominantly will be in that VHF and UHF. Now, SATCOM, radar, cell communications, all of those are in those microwave spectrums. Now, this entire electromagnetic spectrum is contested when we start thinking of war and conflicts. And to drive that point home, a Soviet admiral back in the 70s said, "The next war will be won by the side that best exploits the electromagnetic spectrum." Fast forward decades later, here we are with the war in Ukraine, and there's a significant uptick in the use of this electromagnetic spectrum. Now, electromagnetic warfare is a military action that uses electromagnetic waves to control the electromagnetic spectrum or to attack the enemy. Now, EW could be used to destroy, degrade, or disrupt an adversary's electromagnetic spectrum, but it also could be used to detect an adversary's electromagnetic signature for the purposes of direction finding or geolocation. Now, with this war in Ukraine, we can see that we lost the electromagnetic spectrum dominance globally. Now, that being said, we can still control that electromagnetic spectrum in our local operational areas. Here we have a picture that depicts the electronic signature of a battalion-sized element. And pretty much what this says is the enemy can see us. Now, in the past, we've used things to mitigate these detection efforts. We have terrain masks. We have lowered our energy signals. We have spoofing, jamming, all of those things. But to truly protect ourselves, we need to understand what our electronic signature is. So we have this EW threat, which is now coupled with this shift to a higher intensity and more of a potential for a near-peer combat operation, which is going to bring with it more casualties and increased medical evacuation times to definitive care. Now, the U.S. government is estimating between 60 and 70,000 in military losses for Ukraine during this war. And with rough math, that's 51 people a day. So as we look at potential for more casualties and increased medical evacuation times, saving lives on this new battlefield are going to require more advanced forward care. Now, to optimize that care, Joint Trauma Systems has called for development of a smaller, lighter, and less energy-intensive medical equipment for forward use. Now, portable handheld ultrasounds meet these requirements. Handheld portable ultrasounds have been utilized by SAR for over a decade. But recently, the U.S. Army Research and Development Command, or Medical Command, has started to field 3,500 portable handheld ultrasounds for those far forward units. And those are going to be going to our Roll 1s and Roll 2s. So these handheld ultrasounds support advanced critical care in those far forward environments. But at what risk? Up to this point, the electromagnetic signature of these portable handheld ultrasounds have never been measured.
Thank you, Master Sergeant Tomei, and congratulations again on starting medical school in just 2 months. My name is Captain Maya Alexandre. So to answer the question about the electromagnetic signature of portable and handheld ultrasound systems, I reached out to the Joint Electromagnetic Warfare Center, which partnered with us on this pilot project. The Joint Electromagnetic Warfare Center, or the JUC, has been measuring the electromagnetic signatures of the medical element, and they shared with us models that they had developed of military medical operations. Now, an electromagnetic signature is a function of power and frequency. The specifics of any particular electromagnetic signature depend on many factors, including terrain, weather, and the congestion of the surrounding electromagnetic spectrum. The spectrum analyzer used also has an impact. These models were developed using a commercially available spectrum analyzer, and these signatures would be detectable to adversary. What you're looking at is a model that shows that on the terrain of Fort Cavazos, a 50-watt radio broadcasting at 30 megahertz, as would be typical for a radio used in medical evacuation, has an electromagnetic signature greater than negative 90 decibel milliwatts. That's the red area. Has an electromagnetic signature greater than negative 90 decibel milliwatts that can be seen for 50 kilometers. This model shows you that on the terrain of Fort Cavazos, a Wi-Fi transmitter on a low setting of negative 10 decibel milliwatts, as would be typical for the near-field communications capacity of a Wi-Fi enabled medical device like a patient sensor or a patient monitor, has an electromagnetic signature of greater than negative 90 decibel milliwatts, that's the red area, that can be seen for about 1/10 of a kilometer. And this model shows that a Bluetooth transmitter on the terrain of Fort Cavazos and on a low setting of negative 10 decibel milliwatts, as is typical for the near-field communications capacities of Bluetooth-enabled medical devices like a pulse oximeter, has an electromagnetic signature of greater than negative 90 decibel milliwatts, that's the red area, that can be seen for about 1/4 of a kilometer. So what about ultrasounds? Ultrasounds broadcast on high frequency between 2 and 30 megahertz, but they're broadcasting sound waves, which are mechanical energy, not radio waves, which are electromagnetic energy. So what part of an ultrasound could give rise to an electromagnetic signature? Well, all ultrasounds convert electrical energy into sound energy through a process called the piezoelectric effect that's accomplished by the ceramic crystals in the ultrasound probe. It was not known if this process, which uses electromagnetic energy, would generate a substantial electromagnetic signature. To find out, I designed a pilot study to measure the electromagnetic signatures of 6 handheld and portable ultrasound systems that are found far forward. These 6 systems are the Philips Lumify, the GE Vscan Air, the Sonosite Edge 2, the Sonosite M Turbo, the Butterfly IQ Plus, and the Cosmos EchoMute. Our methods involve taking all of these ultrasound systems to a semi-remote field in Fort Cavazos, which models the electromagnetic operational environment. Using a Rohde & Schwarz PR200 portable spectrum analyzer, we measured the electromagnetic signature of each ultrasound system at a close range of less than 10 feet, both while the system was on and while it was being used to scan. We had intended to develop models of the electromagnetic signatures like those that you saw for the 50-watt radio and for the Wi-Fi and Bluetooth-enabled medical devices. But the electromagnetic signature of all of the ultrasound probes was so insignificant that modeling could not be performed. What follows are the results reporting the technical parameters of the electromagnetic signatures. So what you're looking at is a screenshot of the spectrum analyzer. I'm going to show you a bunch of screenshots, and because they are zoomed in differently, you can't just compare the signatures by eyeballing them, so I'm going to give you the measurements. For those of you who don't work with spectrum analyzers every day, here's a quick overview. That white line is the sensitivity at which the spectrum analyzer was set here, negative 135 decibel milliwatts. Now, most commercial spectrum analyzers cannot detect anything smaller than negative 110 decibel milliwatts, but this spectrum analyzer can detect up to negative 140 decibel milliwatts. None of the signatures that we measured was larger than negative 110 decibel milliwatts. The red arrow is helpfully pointing to the signature, and what you're seeing in that black area at the top is the signature as a snapshot. That's the spike. The purple area at the bottom shows the signature over time. So what you're seeing is that blue line, that is the signature over time. The key points in all of the, I'm going to show you these screenshots. The key points in all of them are that the electromagnetic signatures are essentially identical and are barely visible over baseline at less than 10 feet. Now, this distance is important because in ideal circumstances, radio frequency follows the inverse square law, which means that when you double the distance, the received power is 1/4. So at 20 feet, the received power is going to be 1/4 of the received power that produced this signature, which means the signature will be even smaller. So this is a signature for the Sonosite Edge 2 curvilinear probe. It was detected at negative 137 decibel milliwatts. It was barely perceptible over baseline. And what you can see is that the signature was stable over time. And you'll notice that there are some other signatures right next to it. These are probably very small signatures from radios. And the signature of the Sonosite Edge 2 curvilinear would most likely be taken to be just another radio. The electromagnetic signature of the Sonosite N Turbo linear probe was detected at negative 135 decibel milliwatts. It was barely visible over baseline, and the baseline here is depicted by that red line. The Butterfly IQ Plus probe had an electromagnetic signature that was detected at negative 135 decibel milliwatts. It also was barely detectable over baseline. But as you'll see, those red arrows in the purple field, they're just drawing attention to the fact that the signature over time is a little bit more pronounced than the signature that we saw with the Sonosite M Turbo and the Sonosite Edge 2. That's probably because at the time the signature was taken, the Butterfly probe was transmitting pulse wave Doppler in the 5 megahertz range. Depending on the shielding on the probe, the pulse wave Doppler may generate more radio frequency interference. The Cosmos Echo Nu probe had an electromagnetic signature detectable at negative 125 decibel milliwatts. Again, hardly visible over baseline. And what you're seeing in the purple area where they drew an arrow to that, so that is likely the operator tuning into the central frequency. So once that central frequency was obtained, it was a stable signature. And again, you're seeing that slightly more pronounced appearance to that signature, which likely represents the Echo Nu probe transmitting pulse wave Doppler. The Philips Lumify linear probe had an electromagnetic signature detected at negative 118 decibel milliwatts. And the Philips Lumify phased array probe had an electromagnetic signature detected at negative 115 decibel milliwatts. Now, these two signatures are the largest signatures that we measure for our ultrasound probes, and they are below negative 110 decibel milliwatts. You'll also notice that these Lumifies had slightly more pronounced signatures, as you can see with the red arrow in the purple field. The phased array was likely transmitting pulse wave Doppler, and the linear probe might just be a little bit less insulated so that the radio frequency interference from the piezoelectric effect is just generating a little bit more of a pronounced signature. Now, what you're seeing here is the GE Vscan Air probe. Its signature was detected at negative 127 decibel milliwatts, but what you're looking at is what a signature looks like when it's masked. Here, the GE Vscan Air probe's electromagnetic signature is overwhelmed by the signature of the radio frequency interference from the trackpad on the ultrasound's system. This highlights that general electromagnetic spectrum interference from tactical computing technology must be factored into the assessment of the electromagnetic signature of any ultrasound probe. So what are the takeaways from our pilot study? Well, all the electromagnetic signatures for all the probes are basically identical and can barely be detected above baseline. There was no difference in the electromagnetic signature between the probe just being on and being used to scan. Best practice is to turn the ultrasound system on for scanning, scan as rapidly as possible, and then turn the system off. This is a pilot study. Additional testing is required, but electromagnetic signature measurement should be part of the procurement process. No unit should be deploying with a piece of medical equipment that they don't know what its electromagnetic signature is, and nothing should be included in the MTO unless it has a known electromagnetic signature. In summary, the electromagnetic signatures of an ultrasound probe, regardless of brand, is negligible and unlikely to be detected above baseline. When paired with a visualization device that is not transmitting or receiving on a cellular or near-field network, the electromagnetic signature of the ultrasound system is likely undetectable. What questions do you have?
That's it for today's podcast. Make sure to go to our website, www.prolongedfieldcare.org. Check out our free downloads and a ton of other helpful information. Grab a bag of our fresh roasted PFC coffee, links in the description below, and stay on the bleeding edge of combat and austere medicine. This is Dennis for the PFC podcast, out.